Hello DjangoCon Europe. It's lovely to join you here in virtual Porto. I'm Adam Johnson and today I'm going to talk to you about how to hack a Django website. This talk is organized around 4 stories of sites getting hacked. The first one comes from Facebook. It was a PICKLE remote code execution attack. Don't worry about what that means, we'll find out in a little bit. This wasn't Facebook itself, but this was a Django-based site that Facebook was running. It was an instance of Sentry. The second story comes to us from GitHub. GitHub also doesn't run Django, but it's based on Ruby on Rails, but the same problem existed inside Django. This was something we'd call a Unicode case collision account takeover. Even longer term, but don't worry, we'll unpack that when we get to it. The third story comes from somewhere I used to work, called YPlan, where we had an HTML injection attack in the admin. This is also sometimes known as a cross-site scripting. So this would be my personal story in here. And then the fourth one is from many different sites that I've looked at. A specific form of HTML injection that can occur when you're templating JavaScript. So let's get started. Story 1, Facebook. This is from a 2018 blog post by a security researcher called Blacklist, who detailed everything in this small attack that led them to collect a bug bounty. And they thankfully gave us a lot of details that we can expand upon. The first step that Blacklist took was to scan the Facebook IP range. Since they've got their own data centers, they've bought an IP range to host all their public servers in. This is public knowledge who owns which sets of IPs, so it's quite easy to find out which servers to scan if you're trying to look into looking at Facebook. Whilst doing this, they made HTTP requests to all these IPs and found an instance of Sentry running. This is a Django-based bug tracking tool, and it looked like Facebook had set it up as a prototype. They thought this was kind of interesting. Sentry tends to include information about the applications it's tracking bugs for, so there could be other information to find a vector for attack. Whilst browsing around Sentry, Blacklist found that it was running with debug set to true. That's Django's debug setting. And it didn't take long to find a bug in Sentry itself that led to an exception backtrace. This is probably something they could even find from the Sentry bug tracker. And from this debug page that Django outputs, they could read all the settings. So Django, when it debugs the settings, it actually tries and filters out the sensitive ones, but doesn't stop a combination of non-sensitive data becoming something that an attacker can use. In this case, 3 particular settings combined to allow a remote code execution attack. These 3 settings were the session serializer setting, and this was set to PICKLE serializer, so being able to read this was a useful piece of information. The second was that the session engine used was the signed cookies one. Rather than storing the sessions in the database on the server, they were being sent to the client in a cookie, and the client would send back that session data with each request. And the third, slightly unfortunate step was the debugging of the secret key. Django does filter out the secret key setting, but Sentry provides a way to override it with its own internal setting in Sentry options, and so the same secret key was repeated there. And because the secret key is used to encrypt the sessions, this is what allowed the attack. So with those 3 pieces of information, Blacklist was able to run a piece of Python code locally with their own copy of Django to load, change, and save the cookie that they were using. They could call the Django core signing function to load the signed cookie data, and they were able to do this because they had the secret key, and they knew that the serializer was PICKLE serializer, which was where the main vulnerability came from. They could then change something inside this data dictionary that got loaded, adding data into the session basically. And here they've used a custom class called PICKLE RCE that we'll see in a second. And then they could dump it back out into a byte string, print that to the terminal, copy that into their browser's cookies, send it to the server, and the server would do the same kind of steps on each request to load and check the session data. The unfortunate thing comes from the PICKLE RCE class. So PICKLE is a serialization module built into the standard library, but unfortunately it's not really a pure data module. It actually is code. Something that you may not know if you're using it somewhere inside your system is that it actually runs an interpreter on load to like a mini coding language inside Python. And you can customize what will run on load. So that PICKLE RCE class that Blacklist implemented, it looked like this. It had only a reduce method, and this is called by the PICKLE serialization method to figure out what functions should be imported and called to load this object back on the other end when deserializing. In this case, the class returned os.system and sleep30. So it says to retrieve this object, call this function with these arguments. Well, we can see this won't return any useful object, but it will execute a command on the server. When we dump this into a series of bytes, which is what made its way into the session, you can see that the POSIX part of the OS module is being used. There's the system string that refers to loading that system function, and then here's the command to pass to it. So if we call pickle.loads on this byte string, it runs the sleep30 command. You can get Pickle to do whatever you like. You could make it create HTTP requests, delete data, dump the database, and upload it to a server you control, pretty much anything you want. The Pickle module does come with a warning saying it's not secure, only on Pickle data that you trust. In this case, technically the data was trusted because it was signed with the secret key, but unfortunately the secret key had been given away. So it was like a two-step weakness. After doing all this, Blacklist was able to claim the bounty. Facebook responded very quickly. They took only 18 hours to patch the system and paid out the bounty 2 hours after that. As far as their bounty program goes, this was a lower tier bounty. If any user data had been at risk, if this wasn't a prototype Sentry instance, they would pay more. So what can we learn as aspiring Django website hackers from this? Well, there's really a few things to take away here. First, we can try and look for the debug mode being set. An easy way to do that is to try and browse to URLs that you're pretty sure don't exist. And if you get back a 404 page, that would be Django's debug 404 page. Then you might also want to try and force a crash by pushing untested data and then get a 500, which will output all of the settings that you'd like to inspect. It's also worth looking for things that seem to be using Pickle. Anywhere Pickle is used, there will be maybe some kind of and you can also build more evil Pickle payloads. In the case of this hack, Blacklist only used the sleep30 one to prove the vulnerability, but you could build more interesting ones that if you don't control when the deserialization happens, they could ping you on your remote server and you could find out when that happened. If you put on our other hats about defending against these attacks, well, the main lesson here is never deploy with debug true. Like, this is something that the Django docs highly recommend against, and we also have the system check framework to guard against it, which you should run on every deployment using manage.py check -- deploy. This will actually exit with a failure code if any setting like debug is set when it shouldn't be. We should also try and avoid using Pickle as much as possible. There isn't a safe mode for it. There are attempts out there to tighten it and prevent it from running completely arbitrary commands, but I think there's normally a way around it thanks to the dynamism of Python. And finally, we should look into deprecating the Pickle serializer from Django. There is an open ticket for this. It would just require a little more work to figure out some corner cases in the sessions framework. Now for story 2. This one comes from GitHub, and it was summarized nicely by the person who found it in a blog post. John Gracey. It was announced at the end of last year. And they found a way to take over someone's account using some features of Unicode. So the first step here was case collisions. And what is a case collision? So in Unicode, all of the letters from all of the scripts that humans use are represented or are planned to be represented. And uppercase and lowercase are not simple concepts. They're not a one-to-one mapping. So you might see on the left here, we have two lowercase versions of the string GitHub that would uppercase to the same GitHub, uppercase GitHub on the right. The first one uses an I without a dot. This is a Turkish letter, and the one on the bottom uses the Latin I with a dot that we're used to using in English. Both these strings map to the same uppercase string. So there's some potential for confusion there, especially if the code we're investigating does a case-insensitive comparison and performs that by uppercasing one string, uppercasing the two strings that it's comparing. In English, there aren't that many case collisions. This is thought to be an exhaustive list of all of the ligatures and letters in Unicode that would collide with some English letters. But we can see there's quite a few combinations still. So if we're trying to find a collision with a string that features a double S, an I, or an S, a double F, an ST, then there are these letters and ligatures on the left that would collide. The dotless I from Turkish, the scharfes S from German, and so on. Having found one of these case collisions, John Gracey managed to register a domain, which was github.com without the dot on the I. All Unicode domains are available for registration now. It depends on the top level provider as to how much they support, but .com seems to support most of them. And they're supported with a system called Punycode, which is an ASCII-based encoding of Unicode because some of the DNS system does not support actual Unicode underneath. So this is the technical domain that was actually registered. And the bug that John Gracey had found was that you could get a password reset for the wrong email address, which allows complete a takeover by just changing the password on that account. So if you went to GitHub's password reset form and you entered John at .github.com, it would search in the database for that string uppercased. It would find John at .github.com and say, okay, that account exists. But then it would reuse the email address input in the form to send the actual password reset. So you could take over the account of someone at github.com or anyone whose email address had a case collision effectively. Once you've reset the password, you get in their account, you unleash whatever chaos you want to do. You could export all their data so you can look through it later, delete the account, pretend to be them, make high-profile commits, etc. This bug was in GitHub, which is in Ruby on Rails, but it also existed in Django contrib auth. It was spotted by technical board member Simon Charette after he'd read about GitHub's exploit. He checked inside Django contrib auth, and there it was. So the fix for this went out on December 18th last year, and it's only in these versions of Django and 3.1 as well that it is fixed. What lessons can we take away here for hacking Django websites? Well, first we can look for targets with Unicode case collisions. If we're trying to hack a website that has an I in it, then we already know that there's a case collision. If not, perhaps we want to look inside usernames for double S's, I's, and anything else that was in that table. It would also be expanded if you weren't looking in English. There's probably other case collisions with letters in different languages. It's also worth knowing other freaky features of Unicode that programmers tend not to account for. For example, there are a lot of characters that look the same, and these have been used in a number of attacks like phishing domains that seem to be from your bank but aren't actually. And since this is a known vulnerability that affects Django, and we could find out, and we know which Django versions it affects, if we could detect a site we're trying to attack's Django version, then we could figure out whether this attack would work without much effort. There are some tools out there for doing this, called like Django version detection, etc. And the main way they work is by accessing a known file, like the admin CSS file, and checking for strings in it that were known to be added or deleted in specific Django versions. This can normally fingerprint the version of Django quite accurately. If we put on a defense hat, what can we do here? Well, I think the main lesson to take away is to upgrade Django. This kind of weird, obscure attack that nobody really predicted, that affects even the best sites in the world, you can't proactively defend against it. But if you keep on the latest version of Django, you will have all of the accumulated wisdom and defense against these. So definitely it's worth subscribing to the Django weblog and keeping track of the latest version. My third story comes courtesy of YPlan, my employer from 2014 to 16. We were an events e-commerce app, and we had several of the usual features that you'd expect, like accounts, the ability to set your name, purchase things and see your purchase list, etc. My colleague Tom Granger figured out that if he added HTML to his name in the app, it would get rendered in the admin. So his first step was to open the app and set his name to Tom, and then a script tag that included alert cat face emoji. Then he just needed to wait. Whenever a staff member would browse the admin, then his cat emoji face would appear, and we would get complaints. What was the problem here? Well, the main problem was within our custom admin code. We'd use this mark safe function, which is decidedly not safe. Our user admin class said to list a few fields. One of these was called full name, which we defined on the admin class as the concatenation of the first name and last name. For some reason, we wanted some HTML wrapping that. So we added the HTML inside that function, and when we called mark safe on the resulting string. And mark safe is needed for this HTML to not get escaped and show as actual literal less than, greater than signs in the HTML. Unfortunately, this meant that we were implicitly trusting all of the data that users could set in their first and last names, which meant anyone putting a script tag in there would get that script executed from within the admin page. All of the HTML that users provided was basically unsafely injected into the admin. This is what we'd call an HTML injection attack, or it's sometimes called cross-site scripting, because you can include a script from another site. The solution here is to use a helper function from within Django. It's called format HTML, and this can take your trusted piece of HTML with format tags similar to how string.format works, and safely add the untrusted user data in at the appropriate points. If we are doing a list of things together, we could also use the format HTML join function. What lessons can we take away as hackers from this? Well, we can try adding HTML to every field that we have control over. It's quite common that there'll be some kind of injection vulnerability, unfortunately. And moreover, it only needs to be in one field that we have control over for it to work. Even if the developer gets 99 out of 100 correct, the one broken one would allow us to execute whatever HTML we like on their website. One way to keep a track of this is to use the beacon resources. If we had script tags with a source or images that refer to different URLs for each field that we put them in, the first one that we see get an actual hit, that could be the one that we know that lets us know which fields are vulnerable. And this is especially important for things like the context we were looking at here, where the actual execution of the HTML was in the admin area that we would never be able to access as a pure customer. Putting on our protection hat, well, I think the first lesson is not to copy any code with mark safe. I think there must be a tutorial out there that we'd copied the admin code from, because I've seen the same pattern appear in several other admin classes since. One thing that has been discussed several times on Django to developers is to rename the mark safe function, because it isn't safe. And perhaps the name is leading people to think that it's safe to use arbitrarily. And the third defense will be through this security header called Content Security Policy. This ties into my talk last year on security headers. And with Content Security Policy, you can tell the browser a policy for blocking resources in scripts and images, etc., that you don't trust. So that would allow you to basically ban the inline script tag that Tom had used to alert the cat emoji and any other sources that you don't trust, and it would never be a problem. And now for our fourth story. This one has happened on lots of sites that I've looked into. As a solo consultant, one of the first things I do on a project is run a short audit. And in pretty much every site I've looked into over the past year and a half, I found some variant of this. It does vary how exploitable it is, but it's a recurring theme. It's a bit of a variant on the last one. Again, we'd include some HTML in a field that we control, and we'd see this HTML get injected later. But in this case, the key is that the HTML starts with a closing script tag. And we'll see why this is important in a second. Normally, there's a view that does something like this. So there'd be some structure of data to be passed through to JavaScript that runs on the page. And that could be like this dictionary here that includes the user's name. And this is being turned into JSON here, a JSON string, passed through to the template in this user.json variable. And then the template inlines the JSON inside a piece of JavaScript. So here we have it happening. JSON is a subset of JavaScript, so this looks like it would be safe. And the pipe safe is needed here. Pipe safe is that function we saw earlier, mark safe, just by another name. That's the template filter version. Well, you might have guessed that the safe is not safe here, because we would get that cat alert appearing from my name. The problem here is that the HTML parses first. So this is the output from that template fragment we were looking at. And at first glance, this looks like a script tag, a single script tag that contains a valid piece of JavaScript in the middle that sets the user with a name, and then there's some stuff inside the string, but this is all a valid JavaScript string, so it should be fine. Unfortunately, the first impression is wrong. The browser, when it's parsing the HTML, does not parse the JavaScript within it. So this first script tag starts a context whilst the HTML parser is running that's simply looking for a closing script tag, and so it ends at this point. So this first script tag has basically a fragment of JavaScript, and when this gets executed, it would be a syntax error because there's an unfinished string here. Then there's this second script tag that I'd entered in my name, and the JavaScript within this is perfectly valid. It's a call to alert a cat face, so that's what we get. And then there's a trailing piece of code with a closing script tag, and I think most browsers would simply ignore this because they try and parse HTML in a very lenient way. So what's the solution here? The solution is a filter that's actually built into Django since version 2 called JSON script. The way we'd use this is we'd pass our dictionary without JSON encoding through to the template in the variable user here. And then we'd use the filter JSON script with some string as an identifier for the element that it should generate. then our script becomes completely static. It could even be moved to a separate file. And what this does is it retrieves the contents of this script tag using the DOM API getElementById. When this is rendered, it looks like this, which can make it a little bit more easier to understand. So that first script tag coming from the JSON script filter, it declares its type as JSON. It has the ID that we passed it. And within that, there's this JSON dictionary that we pass through. But most importantly, the script, the HTML that defined the script tags has been turned into Unicode element IDs in the JavaScript string. So these will no longer be parsed by the browser as HTML. They'll simply be seen later by the JavaScript parser and turned back into the corresponding elements. The code is using getElementById to look up that script tag, look up the text content within it, and then parse that with JSON. I wrote a blog post on this because it's so important, so you could go check that out. As hackers, what extra can we learn here? The first thing is to look through the generated pages on a site for inline script tags that seem to be passing data through. Anything that contains some data is potentially exploitable. And similarly to looking for other HTML injection attacks, we can try using a closing script tag at the start of HTML that we stuff into fields that we have control over. For protection, well, we can use JSON script or other solutions that don't exist within Django. And we can also use our friend content security policy again to block any resources that we don't trust. Going to squeeze in a quick bonus here for the talk after these stories. So if you are concerned about your site's security, there's a standard out that's fairly new called security.txt. The idea here is that you serve up a file at a well-known URL on your site with a machine-readable format for your contact information if there is a security vulnerability. And this allows researchers who might just happen to be scanning all the websites that they can get access to report issues that they find to you. To serve this out of Django, it doesn't take very much code. Here's an example view that serves the bare minimum security.txt that has a single line in it, that has an email address. I wrote a blog post on serving well-known URLs that uses security.txt as an example. You can go a bit more advanced, and for example, here's the one on my own website, which shows that it was signed with my PGP key and contains several different forms of contact. Nothing remains but for me to say thank you very much for listening to my talk. I'm Adam Johnson, and these are my contact details. The slides for this talk will go up in this GitHub repository. Thank you.
I was thinking during your talk if something like you find another website is still in, for example, the Django admin code in the HTML part, or if someone have scanned the HTML code in Django itself. If you know.
So Tom Granger, who I mentioned with the cat emojis, actually back in like 2015 or something, he moved to Django admin to be fully content security policy compatible. So it's very unlikely there are any major flaws in there anymore, like the thing with HTML injection when passing to JavaScript. There's definitely a possibility, like maybe some function in Django is using mark safe when it shouldn't. But I think these are generally, it's pretty searched through. Like we have a lot of security fixes, so hopefully not.
Okay, thank you.
Hello, Pascal, Marius.
Hey, great talk. Thank you very much.
Thank you.
Yes, the same for me. It was a great talk. Content security policies are really complicated. Do you have any advice or tips for at least a small set of must-haves that you should contain in them?
I think they're complicated because they act like an allow list mechanism, and you can get away by you can still allow inline scripts and still limit the sources for your remote script tags, but that doesn't really add much protection. So yeah, it's kind of annoying to set it up. There is a Firefox extension that you can browse through a site and it will recommend a content security policy out of everything that got loaded. So that can be a good first step. There's also its report only mode. So you can deploy a content security policy and have it report to a third-party server whenever a browser detects something was loaded that shouldn't have been, and that can help you form a good CSP. There are a couple services that do this. I think Sentry does, and one by Scott Helm called
Report
URI. Yeah, exactly. Yeah. I don't know. Pascal might also have some experience setting this up.
I'm just annoyed by it. I'm deeply disappointed. I tried to do it for my website, but it's still in the report only state because I included Google Maps, and there's no point in activating it if you have Google Maps allowed, because their JSON-P endpoint just allows for anyone to execute arbitrary JavaScript. And I'm really annoyed. It was very complicated to get Google Maps running in the first place, and it's upsetting.
Yes, it's surprising, isn't it?
Yes, come on, Google.
Thanks. As you can see, my kids are here, so it's hard to ask questions. Thanks again.
Appreciate the effort.
So Adam, you show the use of JSON script tag, and the one I tried to suggest to Pascal before, but I think is the main case, the case he provided to show to us it was a bit different. I don't know if there is something not good in inline JavaScript in the HTML page.
If there's something not good.
Yeah, because
you mean
Pascal
in my example?
Yeah, Pascal suggests not to use inline JavaScript in the HTML. I don't know if something in general.
That is good advice. If you're using content security policy, you'll want to activate its feature that disables inline scripts, because they're normally emblematic of an XSS attack, like this injection thing. So in my example, I was just keeping it simple, but yes, it would have been better that I used a separate script file.
Okay, thank you. Now
I think I recommend it in my blog post. Yeah. Pascal, I was wondering if you have security.txt file set up on your site.
No, I did not. Actually, I just learned from your talk about that. That's really cool.
I think it's still pretty new and unpublished. But yeah.
It's really cool, and that's definitely something I'm going to share with my colleagues. That's definitely a takeaway, and it's really cool. I will do that for sure.
I think I've received one notification so far from someone scanning the web, And they told me
cool.
like I don't have a DMARC record set up for my email.
Ah, well,
Which is
okay.
like, I'll go do it, I guess, but it was a bit spammy.
But cool, yeah. I was very impressed when I saw that. I will for sure do that.
There is something missing from the DjangoProject.com website.
What? A security.txt.
The security.txt. Maybe we can add it.
Yep, that should be an issue on Django project repo.
So I think your talk was the last one of the day.
Indeed, yep. I think it's time to go join the closing remarks in like 1 minute.
Okay.
Thanks for
So
Adam.
thanks again for the talk. Bye.
Thank you all. Cheers.